Hello. Hi. Hope you're all well at home. I'm doing okay. My family and I are doing okay. And I think this is our new classroom here for a little while yet. Um, hey, so we've been working towards this topic, stoichiometry. Um, this is going to include writing balanced chemical equations for all top five types of reactions, and it will also include the all the mole conversions, molarity, and the ideal gas law that we've learned just recently. So if you need to review the types of reactions, there's something on my blackboard. Click on types of reactions. There's a help sheet there. I might send out another worksheet for you to practice. It's going to be imperative that you can write balanced chemical equations for all five types of reactions. So I have an example here of course, you recognize that's a combustion reaction, and that's a combustion of methane. And we're going to finally use these balanced chemical equations. What this tells us is that for every one molecule of methane, we need 2 molecules of oxygen. And if we had 1 molecule and two molecules of oxygen, we would get 1 molecule of carbon dioxide and 2 molecules of water. So those coefficients just tell us how much, in this case, how many of each reactant we need, and then it tells us, it predicts how much product we'll get. So we know, counting by molecules doesn't make sense. So we could say, let's say we have 1,000 molecules of methane. Well, we would need 2,000 molecules of oxygen. We would get 1,000 molecules of carbon dioxide. Of course, we'd get 2,000 molecules of water. Well, we know chemists use something else to count. Chemists use the mole. So let's use the mole instead of number of molecules. So what this balanced chemical equation says is that for every 1 mole, for every 1 mole of methane, we need 2 moles of oxygen, and we would get then 1 mole of carbon dioxide and 2 moles of water. So these coefficients are mole ratios. If you don't see a coefficient, there's a 1 there. So we're going to take advantage of these mole ratios. So let's do a mole-to-mole problem, pretty simple stoichiometry problem. Let's say we have 0.2 moles of methane, and we have an excess of oxygen, so we have plenty of oxygen to burn all of this. Let's see if we can figure out how many moles of water we would get. So we would start with what's given, 0.2 moles of methane. And this is what's new. This is the new part of this unit. We're going to use this mole ratio. So we know for every 1 of these, we get 2 of these. So where do you think the 1 needs to go? The 1 mole of methane, needs to go here. 1 mole of methane. And for every 1 mole of methane, we get 2 moles of water. So we're just going to simply multiply by 2. We're going to get 0.4 moles of H2O.